In this section, we're going to talk about more techniques for evaluating limits. Last time we talked about direct substitution, where if you have a limit, you can plug in for x whatever x is approaching. Sometimes that doesn't work out though. Let's take a look at this example. The limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. If I were to plug in -3, this would look like this. -3 squared plus -3 minus 6 all over -3 plus 3. Well, this is 9 minus 3 minus 6, which is going to be 0, over -3 plus 3, which is also 0. 0 over 0 doesn't really help us with anything. This is undefined. So we would venture to say that there's no limit. But that's not necessarily true. Because if I take a look at values approaching -3 from the left and right sides, this is the table that I come up with. At x is -3.01, the function is -5.01, and x is -3.001 gives us -5.001 for the function, and -3.0001 for x gives us -5.0001 for the function. From the other side, -2.99, if I plug that in, that'll be -4.99. -2.999 gives me -4.999, and -2.9999 gives us -4.9999. But then at -3, it's 0 over 0. But if I take that one part out, if I just take -3 out of there, I see that I'm converging to -5. So as long as the left side and the right side are still converging to the same number, that limit can still exist even if direct substitution fails. So how can we do this algebraically then? There's a technique called the dividing out technique. Let's take a look at that same limit. The limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. Begin by factoring the numerator. X squared plus x minus 3. This could factor to a set of binomials here. I've got x and x. And let's see, to make a +1 here, but a -6 over here, I'm going to need x plus 3 and x minus 2. And this is all over x plus 3. Well, now I can see I've got an x plus 3 on top and an x plus 3 on the bottom. I can divide these out, and I'm left with x minus 2. So this limit, as x approaches -3 of my original function, is the same as the limit as x approaches -3 of just x minus 2. Now I can plug in my -3 here, and I'll get -3 minus 2. This is going to be equal to -5. So the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3 is -5. Now this should be used when you try to use direct substitution and it produces a 0 in both the numerator and the denominator. That expression 0 over 0 is called an indeterminate form because from that alone you cannot determine the limit. Here's another one. Find the limit as x approaches 1 of x squared plus x minus 2 all over x minus 1. So first, try to plug in 1. Let's see, 1 squared would give us 1 plus 1 minus 2. So 1 plus 1 is 2, minus 2 is 0 on top, and then 1 minus 1 on bottom is 0 on the bottom. So this is 0 over 0. There's an indeterminate form, which means that there's probably something that I can do. Let's try factoring the top again. X squared plus x minus 2. This is the same as, let's see, set of two binomials, x, x, and I'm trying to get a positive x, but a minus 2 here. So I'm going to have plus 2 and then minus 1. And this is all over x minus 1 on the bottom still. All right, top has an x minus 1, the bottom has an x minus 1. These will divide out, which tells me that the limit as x approaches 1 of my original function here, x squared plus x minus 2, all over x minus 1, this is the same as the limit as x approaches 1 of just x plus 2. Now I'm ready to go ahead and plug in my 1. This is going to be 1 plus 2. So this is 3, which tells me the limit as x approaches 1 of my original x squared plus x minus 2 all over x minus 1 is 3. This isn't the only tool that we're going to talk about today, though. Another way to find the limits of some functions is first to rationalize the numerator of the function. This technique is called the rationalizing technique. Rationalizing the numerator means multiplying the numerator and denominator by the conjugate of the numerator. Now, when you multiply the numerator and denominator by the same thing, you're effectively multiplying by a special 1. So you're changing the way that this looks without changing the value that you've got here. So let's see. I've got the limit as x approaches 0 of the square root of x plus 1, and then minus 1 outside there, all over x. Let's try direct substitution. If I plug in 0, I'll get the square root of 0 plus 1, so that'll be the square root of 1. So that's 1 minus 1 is 0 on top, all over 0 on the bottom. So 0 over 0, this is an indeterminate form. That means that there's probably something I can do here. We're going to try rationalizing. So let's multiply the top and the bottom by the conjugate. The conjugate is the same thing that you see, but change the sign in the middle. So the conjugate of the square root of x plus 4 is the square root of x minus 4. Therefore, the conjugate of the square root of x plus 1 minus 1 is going to be the square root of x plus 1 plus 1. I'm going to multiply by this to the top and the bottom. Okay, for the top, let's do a box here. All right, so this will be the square root of x plus 1, and then minus 1 times the square root of x plus 1 plus 1. Here, this will be, for the first cell, I've got the square root of x plus 1 squared. Of course, the square root of something squared is just itself. So this is going to be x plus 1. Here I'll have the square root of x plus 1 times a positive 1. So this will be a positive square root of x plus 1. And then that times a negative will be minus the square root of x plus 1. Lastly, negative 1 times 1 will give me negative 1. Combining like terms, those will subtract out. I've got a positive square root of x plus 1 and a negative square root of x plus 1. So what do I have here? This will be x plus 1 minus 1 on top over, I'm going to leave this as x times the square root of x plus 1 and then plus 1. Then on the top, I've got 1 minus 1. So those will subtract out, leaving x over x times the square root of x plus 1 and then plus 1. And now I see that I've got an x on the top and an x on the bottom. Those I can subtract out. I'm left with 1 over the square root of x plus 1 plus 1 at the end. Now I'm ready to take my limit. Go ahead and plug in 0 for x. So if I do that, this will be the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1 is equal to 1 over the square root of 0 plus 1 plus 1. Well, the square root of 0 plus 1 is 1, so that'll be the square root of 1 is 1 plus 1. This is 1/2. Since the limit of this is 1/2, that means the limit of my original x approaches 0 of the square root of x plus 1 minus 1 all over x is 1/2. All right, we've got one more example. Let's take a look at that one. Here I've got find the limit as x approaches 4 of the square root of x minus 2 all over x minus 4. Let's try direct substitution just to make sure it doesn't work. Plug in 4, that'll be the square root of 4 is 2. 2 minus 2 is 0 on top. Over 4 minus 4 would be 0 on bottom. 0 over 0, that's an indeterminate form. Means there's probably something I can do. Okay, let's multiply by the conjugate of the top. That means we're going to multiply the top and the bottom by the square root of x plus 2. Off to the side, we'll make a box. And as you get better with these, you might find that you no longer need to do this step. But for now, I think it'll be nice for us to do that. So I've got the square root of x minus 2, and I'm multiplying to the square root of x plus 2. Here I'll have the square root of x squared, or just x. Here I'll have plus 2 times the square root of x, and here I'll have minus 2 times the square root of x. And lastly, minus 4. Okay, let's subtract out and write what's left. So I'll have x minus 4 on top over, on the bottom, I'll leave this as x minus 4 and then times the square root of x plus 2. And I can see that I've got an x minus 4 on the top and an x minus 4 on the bottom. So we can divide those out. And what I'm left with is the limit as x approaches 4 of 1 over the square root of x plus 2. Let's go ahead and plug in. So this will be 1 over the square root of 4, and then plus 2. This will be, the square root of 4 is 2, so 2 plus 2 on the bottom makes 4, 1/4. So the limit, as x approaches 4, of my original square root of x minus 2 all over x minus 4 is 1/4. The dividing out technique and the rationalizing technique are powerful tools that'll help you with finding limits where you normally couldn't through direct substitution.